The new section is entitled Geometric Random Variables. Geometric random variables. Okay, suppose a few things. The trials are independent. That is, the outcome of one trial does not affect the other trial. Okay, I don't know why that line came in, so let's rewrite it. Like I said, the trials are independent. One outcome does not affect another. Suppose the probability of success is equal to P, and P can't be extremes. That is, it must be bigger than 0, it can't be 0, and it also must be less than 1. Okay. Perform trials until the first success. Perform the trials into the first success. Let the random variable x equal the number of trials until the first success. Okay. So, what is the probability that the number of trials is n? Well, if you think about it, the last trial is going to be success. That happens with probability p. The rest are going to be failures. 1 minus p. There's going to be one success and how many failures? Well, you have 1, 2, 3, up to n minus 1, and then n. These first n minus 1 will be failures. So you're going to have n minus 1 failures. So it's 1 minus p, which is also known as q, to the n minus 1 times p. And this formula should somewhat be obvious. Remember, when you have independent trials, you multiply the probability of the outcome of the first trial by the probability of the outcome of the second trial times the probability of the outcome of the third trial, and so on. And that's just what I did. The first n minus 1 probabilities, since they were all failures, all happen to be 1 minus p. Okay. Now, let's prove that this really is a random variable. What is the summation as n goes from 1 to infinity of the probability that x is equal to n? That is, the probability that x is 1 plus the probability that x is 2. That is, the probability of the first successes on the first trial, or, that means plus, the probability of successes on the second trial, or the probability of successes on the third trial, all the way up to infinity. Now, why don't I start with 0? Because it's going to be kind of hard for the first success to happen on the 0th trial. If the 0 trial, you didn't do anything yet. You didn't toss the coin yet. Okay. So, I'm going to write this down. The summation as n goes from 1 to infinity times this. But I know what that is. It's right in the line above. It's this. Probability that x equal n is this. So we have 1 minus p to the n minus 1 times p. Since we're summing over n, and this factor has no n's in it. We can pull it out in front. The other factor, 1 minus p to the n minus 1, clearly has n's in it. Now notice that when n starts, it's 1. This power is 0. This power must start at 0, and it ends at infinity minus 1, which is infinity. That is, I can just rewrite it starting n equals 0, 1 minus p just to the n. So when n is 0, that power is 0. And I go up to infinity. Now 1 minus p is between 0 and 1. Because if you have 1 and you take away something between 0 and 1, you'll have less than 1 left over. If you have $1 in the bank and you take out p dollars, p is more than 0. That is, p is not 0. That is, you won't still have $1 less. You'll have less than $1. And since p is less than 1, you're not taking all of it away. You have $1, but you're taking out less than $1. You will have less than $1 left. That is, this is less than 1. This is a geometric series. The p stays in front, and then you get 1 over 1 minus r. Remember, this is r to the n, where r is 1 minus p. You get 1 over 1 minus r. P, now what's in that denominator is p. 1, 1. Take away 1 is 0. And then you take away negative p. That is, you add p. 0 plus p is p. And yep, this is good old 1. So it is valid. Okay, let us try some problems. Remember, I used in this last problem that the summation of r to the n as n goes from 0 to infinity is 1 over 1 minus r if r is between 0 and 1. And the big difference, this thing come out nice. The big difference between our problem and the one I just wrote down is r is p. No, actually, that's not true. R is 1 minus p. R is 1 minus p. Instead of r, I just put 1 minus p. Instead of r, I put 1 minus p. Okay, wonderful. Now let's do a problem. Now, in this problem, let me give the lemma that we're going to use up front. We're going to talk about the summation of r to the n again. But this time, n doesn't start at 0 or 1. It starts at k. And it goes to infinity. And you can prove that this is r to the k over 1 minus r. That's just something that's known. Basically, the summation as n goes from k to infinity, you could say that this is the summation as n goes from 1 to infinity of r to the n minus. Now, I only want to go from k to infinity. But so far, I have 1, 2, 3, k. The number before k is k minus 1, k plus 1, forever. I only want those. But right now, what I wrote down is everything. So I need to take away those. I need to take away the summation as n goes from 1 to k minus 1 of r to the n. And if you use the formulas from 1 to infinity on these, you will get this result up here. Work it out. Prove it. Don't accept anything I tell you or your teacher tells you. You prove it. You convince yourself that it's right. And the bonus you get for that, if you can prove it, then anytime you need it, if you forgot this formula on the top, you can rederive it. Okay. Suppose you have an urn, and this urn has W white marbles and B black marbles. All the same size. They're all the same size. Okay, so you want to select marbles until the first white marble is chosen. Okay, you need to replace each marble that you selected. Each marble selected. Okay. Now suppose you're asked, what is the probability that A exactly N drawers are required, needed, and part B, at least, I have K in my mind, at least K drawers are needed. Okay. Now, the first thing I want to talk about is why we should say that we replace the marbles. Okay, why must we replace the marbles? Well, first of all, you don't have to replace the marbles, but to be a geometric series, or a geometric random variable, you must replace the marble. And the reason is let's suppose you don't. Suppose you get a black first. Well, there are black marbles, and in total, there's W plus B marbles. Now, if you don't replace that marble, then what's the probability that the second one be a marble? Well, there are no longer B marbles. There's one less. And in total, there are no longer W plus B marbles. Why? Because we took away one. Notice these two probabilities are not equal. Why are they not equal? Because they're not independent. The trials were not independent. What happened after the first trial certainly affects what happened on the second trial. It changed the probabilities. But now, if you replace that marble, after you pick the first marble, the probability that the second one be a marble, well, there's no need to take away the one. There are B black marbles left. You took one, but you put it back. There still are W plus B marbles. You didn't take away any, or you have the same amount you started with. Now, these two probabilities are the same. The outcome of the first trial did not affect the outcome of the second trial, which won't affect the outcome of this third trial, etc. Okay, now, what is it? So let X equal a number of drawers needed. The probability that the random variable X, the number of drawers needed to get to the first white marble, suppose we want it to be N trials. That means we have N minus 1 failures, and we have 1 success. Okay. And each of the failures have the same probability. That is, I know whatever the probability of failure is, and raise it to the n minus 1. Now, what's the probability of failure? Well, x is a white ball, so we got a black ball. It's the probability of getting a black ball. Well, there are b of them, that's the numerator, and the denominator is the total number of outcomes. You can have drawn from any of b plus w marbles. What's the probability of success? The probability of getting a white marble. Well, there's w white marbles, and in total there are b plus w marbles. And that will be the answer. Okay, let's try to get some more space. Now, that was part A, of course. Exactly, n drawings. What if you want at least k? So, the probability of at least k draws, well, this is going to be a summation. It's going to be the probability that x is n. I'm going to add up many, where n can be from k to infinity. From k to infinity. Well, this is the summation as n goes from k to infinity of the probability that x is equal to n. Well, we just did that one. We have b over b plus w to the n minus 1 times w over b plus w. And this is the one to clean up. I'm going to erase all of this material. I'll leave the formula on top. And I notice I do have one error in the no, everything's fine. Okay, so what we need to do, I'm just going to recopy this down. It equals the summation as n goes from k to infinity of b over b plus w times, to the n minus 1, times w over b plus w. There are two factors. Factors are things that are multiplied. The first one does have n in it. The second one does not. So I can factor the second factor out. W over b plus w times the summation as n goes from k to infinity of b over b plus w to the n minus 1. Okay. Now, our formula says that we start at n. Okay? So, I really like to rewrite it. We start, the power should just be n. Okay, the power should just be n. B plus w times the summation. Now, we start at k. That is, this will be k minus 1. Now, if I want the power to just be n, then n should start at k minus 1. When I plug in that value of n in the power, I get k minus 1. And we can still go to infinity. Okay. So this is equal to this w over b plus w times the summation. Now, r is now b over b plus w. And just for the record, r had to be less than 1. It had to be less than 1. Well, the numerator is b, and the bottom is more than b. It's b plus w. Well, as you know, if the denominator is bigger than the numerator, you're less than 1. Okay. Now, the big difference here is instead of k, we have k minus 1. So I get r, which is our b over b plus w. I get r to the starting value. Remember, k is now k minus 1. Divided by 1 minus r. 1 minus r. r is b over b plus w. Okay. So I'm going to make one change. Instead of 1, I'm going to write b plus w over b plus w. And let me erase the bottom. I need even more space. It's a long problem, but it's very, very doable, providing you know that formula that is on the top, the one that I started off with. Okay. So I have the w over b plus w times b over b plus w to the k minus 1 divided by, now in this subtraction we have the same denominator, so I add the numerators, or subtract in this case, b plus w minus b. The b's cancel. I just get w over b plus w. And what do you know? This cancels out, and the final answer is b over b plus w to the k minus 1. That's the probability that it will take at least k draws before the first white ball is chosen. Okay. Like always, we should be able to prove the expected value and the variance. Okay, find the expected value of a geometric random variable. Find the expected value of a geometric random variable. Well, by definition, e of x is equal to the summation of x times p of x. And remember, x is the number of successes x is the number of trials until the first success. And that could go from 1 to infinity. That can just keep going from 1 to infinity. So that is why we are going to sum up from 1 to infinity. The number of trials can go from 1 to infinity. X is n, and x is n. The probability that the random variable is n. Okay. Summation is n goes from 1 to infinity. N is just n times the probability that the first success is after n trials. Well, that means you have n minus 1 failures and then a success. And if you notice, we have 3 factors. Only the last one has nothing to do with n. The first one clearly has to do with n, because as n changes, so does that. And the second one has to do with n, because the power changes as n changes. So the p can come in front. We have the summation of n times 1 minus p to the n minus 1. It then goes from 1 to infinity. Now, if you look at that, that's the derivative. Well, how about, to make things a little bit simpler, for right now, we call 1 minus p q. That's the derivative of q to the n. The p still in front, the summation, but this piece is just the derivative with respect to q, because that's the variable, of q to the n. And then goes from 1 to infinity. Now, we have this rule for derivatives, that the derivative times the derivative of the summation of q to the n, and then goes from 1 to infinity. Okay, something seems to be bothering me. Okay. So this is equal to p times the derivative of that. Well, that's just 1 over 1 minus q. The summation from 1 to infinity of q to the n, geometric series, is 1 over 1 minus q. Well, there's the p in front. The derivative of 1 over 1 minus q, the derivative, well, think of it as 1 minus q to the negative 1. And if the derivative, you take the derivative of that, you bring down the exponent, you keep the 1 minus q to the same, you make the power 1 less, then you take the derivative of what's inside, which is negative 1. Negative 1 times negative 1 is 1 times this. Since the exponent's negative, I can put it in the denominator. It is 1 over 1 minus q squared. 1 minus q is p, so it's 1 over p squared. And kill off 1p on top, 1p on the bottom, you get 1 over p. The expected value of a geometric random variable where the probability of success is p is 1 over p. Okay. Let us make sure that this makes sense. If x is a random variable for a geometric, we have that the expected value of x is 1 over p. Now, suppose you toss a coin. How many times do you expect to toss a coin before you get a head? And you expect to toss it 2 times. You get a tail, then you get a head. In the long run, you get one, and then you get the other. You expect to toss it 2 times before you get your first head. And the probability of success, the probability of getting a head, is 1 over 2. That's my p. So I get 1 over 1/2, which is 2. What do you multiply a half by to get 1? 2. Need 2 halves to have 1, which exactly is the expected value. Suppose you toss or roll a die, a single die. How many times would you expect to have to roll it before you get a 6? Well, let's say it's 3. Well, in the long run, you'll get a 1, a 2, a 3, a 4, a 5, or 6. And then a 1, a 2, a 3, a 4, a 5, and a 6. It's almost like you're going to get it that way. It's going to take 6 times before you get a 3. 6 times before you get a 3. 6 times before you get a 3. And the probability of getting a 3 is 1/6. So that's P. The expected value is going to be 1 over P. 1 over a 6, which is 6. Exactly like I said it would be. So the expected value of our geometric random variable is 1 over P, where P represents the probability of success. Next, we do the variance. Find the variance of a geometric random variable. Now, remember, I'll write this on the bottom, the variance of the random variable x is e of x squared, something we don't have, minus e of x, something we do have, but we have to square it. That is, we're going to put most of our energy in finding e of x squared. That's usually the whole job in finding the variance once you have the expected value. Okay, this is going to be like before, the summation, and then goes from 1 to infinity of x squared times p of x. That is, the summation is n goes from 1 to infinity. Maybe I shouldn't have written limits here. N equals 1 to infinity of n squared times p of n. That is the probability the random variable is n. So the summation as n goes from 1 to infinity of n squared. The probability that x is n, well, that's routine. You have n minus 1 failures. Q is the probability of failure. And you have 1 success. And like before, the only factor that doesn't have an n in it, involved in it, is p. So p comes in front. The summation as n goes from 1 to infinity of n squared q to the n minus 1. Okay. This is equal to the summation as n goes from 1 to infinity of p. Now, let's see what that is. If there was just one n here, this is the same as n times n to the q to the n minus 1. But this here is the derivative of q to the n. And you can always put the constant in. This is the derivative of n q to the n. Remember, when you take the derivative of 7x to the 5th, you probably don't do this. You'd multiply 5 by 7, but you can take out the 7 and take the derivative of x to the 5th, which is 5x to the 4th, and you do get the right answer, 35x to the 4th. That is, this constant can be inside what you're taking the derivative of, or you can put it in front. You can interchange it. So you can put the n in. Okay, let's get rid of this, please. So I'm supposed to sum up n times n to the q minus 1, which is just that. So it's times the derivative of n q to the n. And the p Well, actually, I already factored out the p, so let me continue to factor out the p. Let me factor out the p. And like before, you can interchange the summation and the derivative symbol. And due to space, I'm going to get rid of the side work over here. So this is nothing more than this is nothing more than p times the derivative of the summation, and then goes from 1 to infinity of n q to the n. I need to know what that summation is. Now, here's where it gets tricky. And in fact, I even had to look this up. It's not tricky, it's just some cleverness. And people are just extremely clever, and they actually saw this. Okay. We know that e of x is the summation, and then goes from 1 to infinity of n q to the n minus 1 times p. But instead of p, I'm going to write 1 minus q. 1 minus q. Remember, p plus q is 1. So if you bring over the q as negative q, you get p. Okay. Now, out of nowhere, I'm going to multiply both sides by q over 1 minus q. Q over 1 minus q. I do that to the left side. And I do that to the right side as well. Q over 1 minus q, and everything else stays the same. And it turns out that the 1 minus q's cancel, and when you multiply this q by the q to the n minus 1, you get q to the n. You get q to the n. So this is equal to the summation as n goes from 1 to infinity, q times q to the n minus 1 is q to the n times n. But this here is exactly what I have here. That is, this is equal to p times the derivative with respect to q of this. But this is nothing more than that. Q over 1 minus q times the expected value of x. Okay, so now we're there. Very clever person figured that out. Okay. So this becomes p times the derivative of q over 1 minus q times e of x, which is 1 over p. But p is 1 minus q. So we have p times the derivative of q over 1 minus q all squared. So now it's a straightforward calculus problem. Find the derivative of q over 1 minus q. Okay, with respect to q. So you take the derivative of this fraction or this quotient, use the quotient rule, fraction rule. the derivative of the top, which is 1, times the bottom, which is 1 minus q squared, minus the top stays the way it is. I take the derivative of the bottom, 1 minus q. Bring down the power, make the new power 1 less, take the derivative of what's inside, which is negative 1. And all of this gets divided by the bottom, 1 minus q squared, squared. So it comes to the 4th power. Now, this minus makes that a plus. What I can see is between this term and this term, they both have 1 minus q. So I factor it out. Then I write down what's left over. After factoring out one of these, we have 1 left. 1 minus q times 1 is 1 minus q. Plus, after factoring out 1 minus q to the 1, or just 1 minus q, I'm left with q2 or 2q. And this is all over 1 minus q to the 4th power. I kill off one factor of 1 minus q on top, leaving none. I kill off 1 from the bottom, leaving 3. If you have 2q and you take away q, you just have q. Don't forget the plus 1. This is all over 1 minus q cubed. Okay. So, this is equal to p times the derivative of q over 1 minus q, which is what I just did. I got q plus 1 over 1 minus q to the 3rd power. Okay, we're going to clean up that is, we're going to write it down in terms of p's, and we'll be done. Well, we will then have e of x squared, and we'll compute the variance from there. This is equal to p times q plus 1. But q is 1 minus p. That's q plus 1. All over 1 minus q is p to the 3rd power. So 1p on top, 1p on the bottom. 1 plus 1 is easy. It's 2 minus p over p squared. This is what e of x squared is. That's e of x squared. 2 minus p divided by p squared. So now, let me erase a lot. And now we are going to be able to find the variance. 100% using the formula and the information we now know. The variance of x, by definition, is the expected value of x squared minus the expected value of x all squared. Well, we just found e of x squared. It's that. It's 2 minus p over p squared minus e of x is 1 over p, and we square it. Now, okay. So, we have 2 minus p over p squared minus 1 squared, which is 1 over p squared. In subtraction, if the denominators are the same, keep them. Keep it the same. They are the same. 2 minus 1 is 1. Don't forget to take away the p. That is the this is the variance of x. That's the variance of x. And anytime you want to know the variance of x, you can do one of two things. One of three things. You could memorize it. You could look it up in a textbook or the internet. Or You can rederive it just like I did. Trust me, if I can derive this, so can you. Just remember that little trick that we did. Somehow we got the summation of n q to the n to be involving e, the expected value of x. Okay. Let's do two more problems. On a roulette wheel, or a roulette wheel contains the numbers 1, 2, 3, all the way up to the number 36, and the number 0, and then double 0, 0, 0. Those 38 numbers. There are 36 here, 37, 38 numbers. Okay. Suppose you always bet that the outcome will be one of the numbers 1 through 12. You bet on 1 through 12. You bet on 1 through 12. Okay. What is the probability that you will lose the first 5 bets? You will lose the first 5 bets. Now, if you think about it, you're seeing a wheel. The wheel has no memory. That is, these are independent events. The probability you lose the first 5 bets, it will equal, well, what's the probability you lose? What is the probability that you lose? Well, there are 38 numbers, and you are betting on 12 of them. That is, there are 26 numbers that you will lose on. Actually, why don't we just do it this way? What is the probability of success? It's going to be 12 to 38. Divide both numbers by 2, get 6 out of 19. You have a 6 out of 19 chance of winning. So the probability of failure, remember, whatever number I write here should add up to 1. Let the bottoms be the same. 6 plus 13 is 19. 19 over 19 is 1. That's the probability of failure. You want to do 1 minus 6 over 19. 1 right is 19 over 19 minus 6 over 19. Keep the common denominator. 19 minus 6 is 13. Fine. Either way, you're going to get those numbers. Okay. So now you want to have failure 5 times in a row. Simple. There's 13 over 19 to the 5th, which is approximately 0.1500. Talk a little bit about numbers. What's the difference between my saying the answer is 0.15 and 0.1500? Well, the answer is this one is rounded off to 4 decimal places. That is, let x be the real answer. The real answer is somewhere between 1495 and 1505. Notice it can equal the 1495, but not equal to the 0.1505. Well, I have a problem with that. It's wrong. The left one should be 0.14995, and the next one should be 0.15005. Because if this digit is 5 or more, and it is a 5, you have to bump that one up. If this digit is a 5 or above, you have to bump that one up. If you only want to round off to 4 decimal places, any number between 0.14995 and 0.15005, including the left endpoint but not the right endpoint, would round off the point 1500. Now, point 15, call that, well, we'll call it y. That's going to be between 1.145 inclusive and 0.155 not including it. So it's a big difference between those two numbers. The top one's more exact. The top one is more exact. So you really should include those two zeros. Yes, these two numbers are equal, but in some ways they're not. In some ways they are not equal. And I think that's very important that you understand that. I'd be a pain in the neck and take off a point if you just wrote 0.15 for this answer. How about another part? The first win is on the fourth bet. The probability that the first win is on the fourth bet. And remember, the probability of success was 6 out of 19, and the probability of failure was 13 out of 19. So you are going to have 3 failures and then a win. Okay, so you're going to have 3 failures and 1 win. The probability of failure is 13 over 19. Success is 6 over 19. Since the power is 1, you don't have to write it. You want to write it? Write it. And this is approximately 0.1012. That's the 4 decimal places. Okay, this is definitely a type of problem that you should be able to do. Suppose that the winning of a game of the New York Mets is independent. That is, what they did last game is independent of this game. You can't say, they won their last 9 games, they're on a winning streak. The probability they win next game is going to be higher than it was, say, to win the first game. No, let's suppose they're independent. The probability that the New York Mets win a game, suppose, is 4/7. And assume independence. Assume independence. What is the probability that the first win is on or after the third game? They win, the first win of the season is the third game. They lose the first game, they lose the second game, then they win. Well, if they win 4 out of 7 times, the probability that they lose will be 3 over 7. So basically we're asking, what's the probability that they lose the first game, lose the second game, and win the third game? So the probability they lose is 3 over 7, and they're going to do that 2 times in a row, and then they win 4 out of 7. Well, 3 squared is 9 over 7 times, and 7 squared, is 49, times 4 over 7, 9 times 4 is that, 49 times 7. Well, actually, I do 50 minus 1 times 7. 350 minus 7, 343. So 36 out of 343 times, the New York have their first and the third game. Assuming a big one at the winnings and the results of the games are independent, which of course is not true, and that they win 4 out of 7 times. They win a little bit more than half. So, having a good season, you win more than half of the games. You have a good chance of being in first place. But nonetheless, the chances they win their first game is on the third game. The first game they win is game number 3 is a measly 36 out of 343. Okay, and that completes the section on geometric random variables.